Welcome to the Explainer. Today we're taking what usually looks like dense, intimidating chemistry notes and turning them into an actual detective investigation. We're cracking open a fascinating set of handwritten laboratory case files to reveal the hidden world of qualitative salt analysis. If you've ever wanted to trace exactly how chemists unmask invisible elements hiding inside a totally anonymous powder, well, you are in the exact right place. Let's dive in.
Think about it for a second. How do you identify a chemical suspect you can't even see? We're going to treat these notes as our very own detective's notebook to logically narrow down and unmask these unknown salts. Obviously, we don't have fingerprints or DNA at a molecular crime scene. Instead, we have to use heat, specific chemical reactions, and really careful observation to force these mystery compounds to reveal their true identities. Here is our investigative master plan. We'll cover the basics of salt analysis, gather our first clues with preliminary tests, play with some fire in the flame tests, hunt down acidic radicals, extract a confession with confirmatory wet tests, and finally, solve a real chemical mystery. All right, Section 1, Basics of Salt Analysis. Let's establish our suspect profile. Every salt is really just a mashup of charged puzzle pieces called radicals. Identifying these individual pieces, that's the entire game here. The salt itself isn't just one single, uniform suspect. It's a combination of these charged ions. If we can isolate and identify the specific pieces, we completely unmask the compound. Our suspects are basically split into two rival factions. On one side, we have the negatively charged acidic radicals, like your chlorides or sulfates. On the other side, we have the positively charged basic radicals, like sodium or copper ions. Because of this fundamental split, we actually have to run completely different sets of interrogations to identify each type. Moving on to Section 2, First Clues, Preliminary Tests. This is our initial interrogation right at the scene. Honestly, sometimes a quick glance or a careful sniff is all it takes to cross dozens of suspects off your list right away. If the salt is blue, we might be looking at copper. Light green, we're probably leaning towards iron. And the smell is a dead giveaway, even if it's occasionally a pretty unpleasant one in the lab. An ammoniacal smell points straight to ammonium, while a sharp vinegar scent screams acetate. Without mixing a single drop of acid, we already have some incredibly strong leads. Then there's the charcoal cavity test, which is just classic old-school chemistry. It's a physical interrogation tactic, where we blast the salt with a blowpipe on a block of charcoal to decompose metal carbonates, and it gives us fantastic clues. For example, if the residue is yellow when it's hot but turns white when it cools down, boom, you've just unmasked zinc. It's these highly specific, quirky physical reactions that really start building our case. Section 3, Playing with Fire, Flames, Time for the Thermal Interrogation. Now this is where it gets incredibly visual. This crucial cheat sheet maps the exact colors produced in a flame test directly to specific basic radicals. They basically hold up a glowing neon sign confessing who they are. We take a tiny bit of the salt on a platinum wire, hold it in the non-luminous part of a Bunsen flame, and watch. If it flashes a brilliant carmine red, we know lithium is in the house. A golden yellow flame is the absolute, unmistakable signature of sodium. Apple green? That's barium. It's a beautiful way to lock in the identity of those positive ions. Now, for transition metals, we whip out the borax bead test. We heat borax until it swells and melts into this clear, glassy little bead, and then we dip it into our salt. Depending on whether we use an oxidizing or reducing flame, the metal salt forms distinctively colored beads. Cobalt, for instance, will produce a stunning blue bead, while copper might shift from blue in an oxidizing flame to red in a reducing flame. It's incredibly precise. All right, Section 4, Hunting down acidic radicals. Let's isolate those anions. So here's the problem. Heavy metal cations can actually photobomb or completely mask the reactions of our acidic suspects, basically ruining the test. It's super frustrating. But we have a brilliant tactical workaround, the sodium carbonate extract. By following this rigorous 3-step protocol, boiling the salt with sodium carbonate, we literally force the basic radicals to precipitate out. That leaves us with a totally clean, clear soda extract containing only our acidic suspects. Once we have that pure extract, we add dilute acids, and the gases that escape, they're literally confessions. We just watch and listen. Brisk effervescence with a gas that turns lime water milky, that's carbon dioxide, period, proves we have a carbonate. A pungent gas that also turns lime water milky, that points to sulfite.
A brown gas that turns starch paper blue practically screams nitrite. The chemistry is literally speaking to us right here through these escaping gases.
Section 5. The confirmatory wet tests. This is where we extract the final confession.
Preliminary clues are great for building a theory, but to close the case, we need ironclad evidence. And that comes down to manipulating these core solubility rules. Knowing what dissolves and what forms a solid is your absolute best weapon. Since we know almost all chlorides are soluble except for silver, lead, and mercury, we can add a silver nitrate solution. If a thick white precipitate suddenly crashes out of the liquid, we've just definitively confirmed chloride. We are forcing the unseen into the open on command. Let's look at a couple more examples of how we definitively trap these radicals. Take the sodium nitroprusside test. Drop that reagent into a sulfide solution, and bam, you get this unmistakable gorgeous purple complex. Or the famous brown ring test for nitrite. By carefully adding iron sulfate and sulfuric acid, you create a literal brown ring right at the junction of the two liquids. That right there, that is the smoking gun. Case closed.
And finally, Section 6. Solving a chemical mystery. The grand finale. Let's put our entire investigative toolkit to the test with a live, complex case file. We're presented with a mystery starting with a lump of roasted fool's gold, which kicks off a chain reaction of completely unknown compounds labeled A through F. Fool's gold is an iron sulfide ore. When roasted in air, it forms a compound A, which crystallizes into green crystals of B. Right away, our preliminary knowledge kicks in. Green crystals heavily point to an iron 2 sulfate compound.
It looks like a giant puzzle, but we just trace the flowchart arrows one by one. There's a major clue here about a blood-red precipitate named E, formed when compound D reacts with ammonium thiocyanate. Wait a second. From our wet test rules, we know for a fact that iron 3 creates exactly this blood-red complex with thiocyanate. Suddenly, the entire flowchart unlocks. A is iron 3 oxide, B is iron 2 sulfate, D is iron 3 chloride. We just solved the whole thing by applying our rules of observation step by step.
So as you can see, qualitative analysis absolutely isn't just rote memorization. It is a brilliant deductive puzzle just waiting for you to crack it. Every color change, escaping gas, and crystal formation is a direct, visible message from the invisible molecular world. Now that you know how to trace these clues, from the glowing flame tests to the complex flowcharts, you realize that every anonymous substance around us has a specific, identifiable chemical fingerprint. So I'll leave you with this. What invisible elements are hiding in plain sight around you right now? Thanks for joining me on this explainer, and keep questioning the world around you.